It is by Animesh. He's a senior software engineer, and his primary interests are around ML frameworks and system efficiency. Over to you, Animesh. Let's have a round of applause for Animesh.
Hello, everyone. Good evening. Uh, you all look very tired, so without much delay, I'd quickly like to introduce myself. Hello, I'm Animesh Dutta. I'm working as a senior software engineer. Currently, I'm having 4 years of experience working, and I've worked on ML frameworks, compression algorithms, and some visualization tools. So today's talk, I'll be focusing on asynchronous programming, especially for scalable machine learning pipelines in Python. So let's get started. So a quick show of hands, how many of you use Jupyter notebooks? Okay, and how many of you just go on executing one cell after another for fetching, then pre-processing, then training? A quick show of hands. So yeah, that's the traditional ML pipelines which we all follow, which involves first fetching, then pre-processing, and then training our model. But what if I tell you we can do it concurrently using async ML pipelines? So it is fast and furious. It gives you the ability to perform operations concurrently, and you get more time for insights. So that's most about sync pipelines. So the key takeaway is for if you are using asynchronous machine learning pipelines, it's less of waiting and more of creating. So before we dig deep, let's have a quick difference what between synchronous and asynchronous is. If you see, the color codes are nothing but tasks. So in case of synchronous, it's sequential. So once the blue task finishes, the next starts. And you see that there's an arrow for the total execution time. For asynchronous, you can see it can happen concurrently, and the total execution time is quite less as compared to synchronous. So how can you use asynchronous programming in machine learning? There are broadly three main applications from asynchronous programming in machine learning. First and foremost, you can use it for data ingestion. So what I mean by data ingestion is if you are having, suppose, 10 URLs you have to fetch data from, you can do it concurrently using asynchronous machine learning pipelines. Next, we can use it for model inference. So as you know, we have to perform multiple predictions after training. So if you're using asynchronous machine learning pipelines, you can perform multiple predictions simultaneously. And lastly, you can use it for your model deployment so that your model can take care of multiple requests, model requests simultaneously at once. So let's delve deeper into async IO, which is the most important part for implementing asynchronous pipelines in Python. We have three key components for synchronous programming in ML pipelines. So first one being event loop, second one being the coroutines, and third one being tasks. So we'll go deeper into each of them in the next slides. So what an event loop does. Event loop is considered as the backbone of any asynchronous pipeline. So event loop is for picking a task and managing the execution. So in case, if you can consider it like operating system where it is the backbone of any execution. In this case, the event loop picks any task, runs them, and manages their execution end to end. So once the task finishes, it gives control back to the event loop. So if you see a sample usage example I've put, you use the async IO keyword and the run command, and that it starts the event loop and executes the main coroutine. So in a machine learning pipelines, the application you can see, it can be for fetching and processing multiple data models simultaneously. So we heard about coroutines in the previous slides. So what are coroutines, which event loop manages? So any function which starts with the async keyword is a coroutine. So this is like the special functions which Python gives us support, and we can use the await keyword to pause their execution until a task completes. So that's more about coroutines, which is used by event loops. And tasks are nothing but the coroutines which are created with the async task command. So it allows the coroutines to run concurrently, and again, it's totally managed by the event loop. So diagram which will give you a better example. So suppose we have n tasks waiting in a queue. The event loop selects the task and executes it. Once the execution is over, we return the control back to the event loop. Now we would like to focus on concurrent data fetching and processing. So how can we do this? We have data fetching and suppose pre-processing. We define coroutines for each of them. So first coroutines for fetching and coroutines for pre-processing. Then we create a task to run these coroutines concurrently and we're getting the results. So all this by using the event loop in background. So an example workflow, as you can see, we define the coroutines for data fetching and processing. We create the tasks which are required. So suppose a fetching, processing, and training, we create tasks, separate tasks for each of them. And we use the event loop for managing. Next up, we have asynchronous data ingestion or the fetching part of your model. So if you have 100 URLs, right? So if you are running on a Jupyter notebook and you just can't wait for 100 URLs to be fetched and you then begin pre-processing, right? So in case of asynchronous data ingestion, you can fetch from multiple URLs simultaneously. And suppose a certain URL has been fetched, you can start pre-processing it without all the URLs being fetched. So that's one of the main use cases. You have faster data retrieval, and you have efficient resource utilization. So your CPU or GPUs don't sit idle while every task is being fetched. So how do you implement them? You define the asynchronous functions using asyncdef. You create asynchronous tasks for each of them, and then you gather the results. So async.io.gather can help you run. Suppose you have multiple coroutines, so it helps you run them concurrently. We use the async.io.gather function. We'll see in the code later for better understanding. So next we have parallel data processing with fetching. So in case of parallel processing, what we do is we know, right, fetching is an IO operation. So with help of fetching, you can also run your processing or training simultaneously. So you can use your multiple CPU cores for this or the threads so that you can get a better performance. And for heavy CPU intensive tasks, you can have them running together. And the main use case for this is you can maximize your CPU usage. You can have faster execution, like if you have a very large data set, you can have a faster execution speed. And again, the implementation, if you see, we can use both multi-threading or multi-processing for defining the functions. You can divide the workload. So in the coding example, which I'll show you, we have broken the large data sets into chunks so that it can happen. We can show how the separate chunks can be trained and pre-processed simultaneously. And you can use the thread pool executor or the process pool executor to manage these tasks. One key thing to note is you have to make sure that you're following thread shift principles. So in case of parallel processing, you have multiple threads, right? But you have to handle the IO-bound tasks properly as well as the CPU-bound tasks because you'll be using threads which will be using the same memory space. You don't want to corrupt that when you're using multiple threads. So make sure that you manage this properly while you're doing a parallel processing. And a few other thread safe data structures include queue. You can use queues for enabling thread safe tools, and for synchronization tools, you can use locks and semaphores so that you can lock, if you have a critical section, you can lock it using a semaphore so that no other thread can access it again. So I spoke about thread pool executor. Now the limitation of Python, the global interpreter lock. So the global interpreter lock, as you know, it prevents true multi-threading. So in case of IO operation and CPU intensive tasks, it can run parallelly. But two CPU bound tasks can't run parallelly. You can't achieve true parallelism using multi-threading. That's one disadvantage for Python, but yeah, that is being addressed, I think, in the latest versions. We'll come to it. And thread pool executor. So what thread pool executor does is it creates separate threads for each task. So the main event loop is never blocked. You can continue logging or monitoring your performances when your model is being trained. So there's no blocking the main event loop. There'll be separate threads for each task you'll be having. So that's why you use the thread pool executor. You can, if for multiprocessing, you can also use process pool executor. So some of the key considerations which I'd like to highlight is error handling, the first and foremost. So you have to make sure that while you're deploying in prod, you properly handle all the errors which might be there. Because in case of multi-threading, sometimes we can corrupt as it's using the same memory space, we can corrupt some of the memory space, and then again the next thread might be corrupted. So we make sure that proper error handling is there. Next, we have concurrency management. So you can't overload your system, suppose with 10,000 threads while you have maximum, suppose 8 workers. That won't help you much. And the performance monitoring. So you keep monitoring the performance of your machine learning model. So as I mentioned, right, your event loop is free for logging and monitoring. It's different threads that are executing the CPU-bound tasks. So please make sure that your event loop will be taking care of the logging and monitoring part. So here we have a simple case study for fraud detection system. So we will be building a machine learning pipeline that will be fetching, processing, and training chunks of a large data set simultaneously. The data sets involves some transactions. So you have the destination balance, the old balance which was there, and there's a name for the client. And obviously the data, the test data set is a binary label, 1 being fraudulent and 0 being legitimate. So I want you to look into this, the machine learning pipeline which I've been speaking for. So first and foremost, to define your asynchronous data fetching function. Next, you define the asynchronous pre-processing and training function. So for output tasks, you have the data fetching, and CPU-bound tasks are the pre-processing and training. So you can fetch, pre-process, and train chunks concurrently. For true parallelism, you can use multiprocessing. In this example, we're using multi-threading. Next, you have to define the async prediction function, which will, after training is completed, you can use it for getting the label, whether it's a legitimate transaction or not. And then you can perform the prediction on each chunk and finally get the output generated. So how to do the data fetching part asynchronously? So Python provides you the async IO library. So if you see, AIO HTTP is the one which you can use to fetch different URLs concurrently. Again, if you see at the top, we have a semaphore limit. This semaphore limit is used here to control concurrency. You don't want to overload 10,000 URLs simultaneously if you are in a low network area, suppose. That's why you have a semaphore limit to control the concurrency. Next, you have the max workers. So suppose you have many CPU-bound tasks, and you have, suppose, an 8-core CPU. So you don't want many workers. Ideally, you should have same number of workers if you're working on a CPU. You should have same number of workers as the number of cores in your CPU. So make sure you check that before putting the max workers. And then you have the function, which is to get the URLs and fetch the data from each URL. So you have the asynchronous data fetching function there. So I spoke about the semaphore control, and then the thread pool executor, which will be having 8 worker threads, and the asynchronous fetching using AIO HTTP. Next, after fetching, we have the data preprocessing and training of chunks. So it's not that we are waiting for all the URLs to be fetched here. This will be asynchronous. So as soon as, suppose, we get one URL's data fetched, we can preprocess it. As soon as we have the preprocessing, we can have the training of that chunk. So no waiting for first fetching of all the URLs before we start with preprocessing and training, which saves a lot of time, trust me. So how do we do it? We have a async preprocess chunk function here. So we are dropping the column, which is the test data set for test. There is fraud column. And then we use the async i.get event loop dot run in executor. This run in executor makes sure that the thread is run in a separate, this thread is run in a separate thread, and the main event loop is free. This is how we manage preprocessing. Here we are using normal column transformer. I'll share the entire code for your reference. So for missing values, we'll be using one-hot encoding for categorical columns. And for numerical columns, we'll be using the most frequent. So once your preprocessing function is written, you write your partial training function. So why did I mention partial training function here? We're using stochastic gradient descent here, which gives us the option for incremental model learning. So suppose you have trained on one chunk of data, you want to train it on the next chunk, right? So your model will keep tuning as and when it gets the training data. So it's not the one-time learning your model will have. So Python has the scikit-learn library for SGT classifier. You can check it out. So again, here if you see, we are using the run-in executor function again and a lambda function for partial fitting of the model after pre-processing is done for the chunks which we are having. And there are two classes here, 0 and 1, as I mentioned. So pre-processing is offloaded. The CPU data-intensive tasks and transformations can run concurrently without blocking the main event loop. And we can have incremental training of our SGD classifier. So all the functions together, if you see, the fetching, pre-processing, and training chunks concurrently using the semaphores, which I spoke about in the beginning. So you have, suppose, 10 URLs. You're fetching from all the URLs, but as soon as you fetch one of them, you can go to the async def process and train function, which is used, which gets the fetch task as a parameter, and you can control the concurrency using the semaphore, which I wrote there. So you can await, we are using the await fetch task. So if there's no task which is fetched, it will wait that at least one chunk we have fetched, and then only the pre-processing or the training begins. So that's why the await keyword is there. And then once you have that, you can start with your pre-processing and training functions, which I showed you. And then you have the task.append pre-process and train fetch task, so that you have a track of whatever you have trained already, and make sure you delete that chunk of data from the memory so that you don't keep on training on incremental data as you keep fetching. That will again spoil the entire cause of what we used asynchronous machine learning. Again, so run all fetch, process, and train tasks concurrently. We use the gather function here. So what it does, it doesn't allow to start prediction before the training is complete. So it will await on that point. Entire data will be fetched, pre-processed, trained, then only it will go to the next asynchronous prediction function. So .gather helps you for achieving that, so you can fetch, process, and train tasks concurrently. But it will make sure that before predicting, your model is incrementally running trained, and then after training completes, then only prediction is beginning. So here it was, so I trained it on a very small data, and don't go by the accuracy because it was mostly zeros, like all were legitimates mostly. So the accuracy is so high, but you can try it on a different model. We have the precision recall and the reference score here. And the time execution, you can see it's 2.56 seconds. Again, as I mentioned, it was 10,000 odd rows, if I remember correctly. So on a larger data set, you'll be getting more time for this. So if we compare now between synchronous and asynchronous machine learning pipelines, first and foremost metric is the execution time, which will be higher in case of synchronous machine learning pipelines due to blocking I/O and CPU burn tasks. So in case of asynchronous, it will be comparatively lower because you are running it concurrently. Second is the data fetching, which is again sequential, but in case of asynchronous, it's faster because it's concurrent, and pre-processing and training. In case of sequential, it will block the main thread. But in case of asynchronous, it will be non-blocking, so you can allow multitasking in case of asynchronous. Again, resource utilization, if you see, less efficient in case of synchronous, and it's more efficient because it uses event loop in case of asynchronous. So I've listed down some of the gains of asynchronous approach. First and foremost being the faster data fetching, because it is handling multiple HTTP requests concurrently. Secondly, it is effective utilization of the CPU, because it offloads the heavy tasks with the async IO thread. And then again, we have the reduced total execution time for IO bounded tasks especially. Now, so as I mentioned, right, for the concurrent operations, data fetching and pre-processing can happen in parallel, and thus it reduces the wait time, improving the faster overall processing. and we have improved resource utilization. So if you have a GPU, in this case, I'm only using CPU. So if you have a GPU, you can use it in even better in case of asynchronous, if you're following asynchronous principles, which results in a higher efficiency and throughput, and you get a reduced execution time. And the most important part is scalability. So if you have a huge database and there's millions of rows, right? You can train and pre-process simultaneously chunks of data. So in case of synchronous, you have to wait for entire fetching and then only you can start pre-processing. But in case of asynchronous, has a huge advantage which helps you to scale data more. Because you see, you can add more data to it, right? It will still split and handle it in chunks. So you get this added advantage in case of asynchronous. So to conclude, I can mention, as you see, we have a faster data fetching in case of asynchronous ML pipelines. Parallel pre-processing happens, so it allows concurrently to handle large data sets. We can minimize bottlenecks because of this, and we can boost the overall performance of our model. Scalability and adaptive handling. So you can scale effortlessly the asynchronous machine learning pipeline. You don't need to take care of that there's more data which is request which is coming from your maybe peers or something. It will take care of its own, and you can handle the complex pre-processing, multi-thread, complex pre-processing and training on separate threads, and thus you get optimal resource utilization. Future scope. So the code which I've written is again totally on CPU. You can fork it. I'll provide the GitHub repo at the end, and you can use GPU acceleration to further enhance performance. I have a bigger data set, and I have broken it into smaller chunks. So you can use the bigger data set on your GPU to see how your model is performing. Integration with cloud services. You can integrate your pipelines in the cloud. You can use Fast API or any other cloud service provider to test even better. Enhanced error handling and logging. So in this current code, the error handling is not that robust. You can maybe fork my repo and add more robust error handling and logging code. And leveraging GIL disabling for enhanced parallelism. So I would like to highlight on this point. Python 3.13 onwards will have a feature to disable GIL, the global interpreter lock, which allows only, so currently the GIL allows only one thread to change the Python's bytecode at a time. But if we have the option to disable GIL, we'll be able to achieve true parallelism in Python. But it's still in experimental mode, but yeah, it stabilizes in the future versions for sure. So I think that's it from my side. Thank you for being a patient listener. I know it's been a very hectic weekend for you all. So you can check out my GitHub repo. I mentioned the link here, and you can send me a connection request on LinkedIn. I would definitely like to speak to you folks. If you have any doubt on the presentation, or if you want to discuss anything, you feel free to connect. Yeah, that's it from my side. If you have any questions, I definitely like to take them. I think I'm ahead of my time. That's great. Yeah, sure.
Folks, if you have any questions, if you want to ask Animesh anything, you can gather around that mic and we'll take the questions one by one.
Hi Animesh,
Hello.
Ranal here. Hi. I have a question, like main problem comes with the async operation is that the logs that are coming are not rearranged in a proper format. Is there any way that we can improve the readability of the logs?
So if I get your question correctly, you mean that as soon as, are you speaking about the pre-processing part or logs while you're training the model?
Yeah, second one.
The training your model part?
Yes.
Is it? So in this case, if you want better readability of the logs, I would suggest you can create separate logs for suppose separate epochs or separate, if you want a more granular approach, you can create separate logs for each of the epochs, but again, it will be huge storage. So if it's a pet project, if it's a smaller data set, I think you can manage it using totally, if you can print it in one place. But for larger data sets, I think you can, for better understanding, you can write it in 2 separate files for this. Yeah,
Sure. Thanks. Thanks.
no problem. Folks, please feel free to fork this repo. I would love if you want to implement multiprocessing. It currently uses multi-threading in this code. If you want a glimpse of the code, I can show you. I think.
Hi, Animesh. One more question here.
Yeah, sure.
So the training part of the model, right? That
Uh-huh.
is also parallel in this. How
In
is-
this case, so your pre-processing,
Okay.
like fetching, pre-processing, and training is happening concurrently. So
Okay.
you can have parallelism. Suppose if you're fetching and training chunks, that is truly parallel in case of Python, while
Yeah.
we are considering multi-threading.
Okay.
But if you want true parallelism, as I spoke, then you have to go for a first CPU-bounded task. So if you want true parallelism, that is 2 threads. One is pre-processing and one is training. You need to go for multi-processing as of now. Python 3.13 onwards, you will get an option to disable GIL. So once it stabilizes, you'll get to see true parallelism for multi-threading in Python.
Okay. So just to re-clarify one thing,
Yeah.
if I just talk about the training part, right, where
Yeah.
let's say the model weights are getting updated,
Mhm.
at a time, it is getting updated only one at a time, right?
Yeah.
Not multiple threads, right?
So at a time, for multi-threading, it will be one at a time.
One at a
Like your model is getting trained on one chunk, and then the next chunk comes, and it gets updated on the hyperparameters for this coding example. Again, if you change this code from multi-threading to multi-processing, it can be multiple chunks simultaneously.
Sure. Got it. Thanks.
No problem. Any further questions? I'll be here, guys, if you want to have a chat around this. If you want to collaborate, feel free to hit me up. Yeah. I think that's it.
That's it.
I'm 3 minutes ahead.
Thank you so much, Animesh.
Thank you for giving